Hey, PChemsters, this is Mrs. Vandelay bringing you Blankwalle, Chapter 13, Section 6. This is all about reaction mechanisms. And what is a mechanism? It is the series of steps that show you exactly how you go from the reactants to the products, okay? It's a lot like mechanisms in organic chemistry, which again shows you exactly how you go from the first step to the last step, okay? So the reaction mechanism is called a series of elementary steps, so individual steps that must satisfy the two requirements. And we're going to refer back to this a little bit later on. So the first requirement, the sum of the elementary steps must give the overall balance equation for the reaction. This is a lot like, you might want to write this down, Hess's law. Remember how we did Hess's law when we crossed things out to come up with the overall reaction? That's what we're talking about in number one. So write that down. It's like Hess's law. Number two, the mechanism must agree with the experimentally determined rate law. So like what we learned in section 13.3. Rate equals K times the molarity of something raised to a power, perhaps the molarity of something else raised to a power. So the mechanism must agree, and we're going to learn about what does this mean, okay? We have a couple of terms. An intermediate is a species that is neither a reactant nor a product, a final reactant nor a final product, but is formed and consumed during a chemical reaction. An elementary step is a reaction whose rate law can be written from their molecularity based equation or balance equation from the step. All right, again, we'll talk about what does this elementary step mean. What does that mean? So what is this molecularity? Okay, so here we go. Oops, scroll down here. There we go. So molecularity is like what must happen for this reaction to occur. So what collisions must happen, okay? So it's the number of species that must collide to produce the reaction indicated by that step. So a unimolecular step is a reaction involving one molecule. One molecule will probably like decompose as be a unimolecular step, okay? So here, for the example here we have one reactant and you make products. Now you think, well, can two of the same reactants collide and make new products? No, that would be a bimolecular step. So it's a reaction involving the collisions of two species. They can be either the same species or two different species. So notice right here, here's two of the same species and here's two different species. And the termolecular step is a reaction involving the collision of three species, all right? And so here you have to have the right collision of like two A's and one B colliding perfectly to make your product. Or if you have A, B, and C, excuse me, what is really the chances that you have exactly the right A, the right B, and the right C, all in the right orientation to have what was called an effective collision. And notice how this unimolecular step, what is the power that it's raised to? 1. A bimolecular step, what is this subscript raised to? It's raised to a 2. Even in the other one, if you add up the power, so A to the first, B to the first, so 1 plus 1 equals 2. That's a bimolecular step. A termolecular step would be like 3. So notice that the coefficients 2 plus 1 is 3 and 1 plus 1 plus 1 is 3. So the type of molecularity will really determine the overall rate law, if you will, as to what power, the order of that rate. So the rate determining step, let's scroll down here because we talked about that, is the slowest step in a reaction determines the rate of the reaction. That's really important. Highlight this, star this. This is super important. And my analogy is to this. I remember, let's say at a big family dinner, and all the ladies gather and do the dishes. I know this has been a long time ago. And grandma was there. I love my grandma dearly, but she would always want to dry the dishes. That's fine. So all of us are clearing the table and washing the dishes. But what was the rate determining step in this case? It was grandma drying the dishes. She was really slow. So there'd be like a backlog of dishes to be dried waiting for grandma to dry them. So how fast did this whole process take? It was how fast grandma could dry the dishes. Well, what if grandma were the one clearing the table? What do you think? She was old then. What do you think of the rate determining step in that process would be? Again, how fast could grandma clear the table? So the slowest step will determine how fast the whole reaction goes. Hopefully that makes sense. Hopefully my analogy makes sense. Okay. my grandma. All right, so I'm not dissing her at all. Okay, let's go to the next page. All right, so for example, here is my overall reaction. I have some nitrogen dioxide and carbon monoxide, making nitrogen monoxide and carbon dioxide. So going in lab, using Beer's law, using something, we can experimentally determine the rate law. And we notice the rate is equal to some constant times the concentration of nitrogen dioxide raised to the second, okay? So here are my two elementary steps, okay? So my NO are going to collide to make NO3 plus NO. Then NO3 will collide with CO to make NO2 plus CO2. So which is the rate determining step? Okay, let me scroll maybe here. So if it is step one, this step right here, what would be my experimentally determined, rate law here? Well, take a look. I have two NO2s, so it'd be K NO2 raised to the second, and this agrees with the experimental results. This is what we figured out in lab, okay? Well, what if step two was the slow step, the rate determining step? What would be the rate law? Well, it would be rate equals one of these times one of these, all right? That does not agree with the rate determining law, all right? So the second step does not match this. The first step matches this. Therefore, the first step must be the slow step, the rate determining step. Okay. So for elementary steps, what can the coefficients be used for? Well, do you remember what we did back in 13.2 when we found out the rate of consumption and the rate of formation? That's what they can be used for, but unless you know the rate determining step, you don't use your coefficients for the rate law, all right? Hopefully you've made that distinguish, all right? That the elementary steps can be used to determine the rate of consumption or rate of formation like we did in 12 or 13.2, but it cannot be used for writing this kind of a rate law unless you know which elementary step is the rate determining step. Hopefully you wrote something down to help you figure that out, okay? So problem number 28. All right, so problem number 28, this says define the terms elementary step, the reaction mechanism, intermediates, and the rate determining step using the following example, all right? So the elementary step, here we have two of them. This is the first elementary step, and this is the second elementary step, okay? So it's the different steps, the different things you're doing to go from the full reactants to the full products, okay? So these are the mechanisms, these are the how we go about doing that. The reaction mechanism, all right, is really what we just did here. So each individual is an elementary step, put it all together, add your steps together, and that's your reaction mechanism. So what's an intermediate? If you go back and look at the definition, the intermediate is what is first formed and then consumed without being part of the overall equation. So I'm looking over here and I'm looking at NO3 is not in my original reaction, okay? And so notice how NO3 is first created and then consumed. So I call both of these, here we go, oh, come here. I call this and I call these, it's my intermediate, okay? Because it is consumed, or sorry, it's formed and then consumed. All right, so those are my intermediates. Something else I should probably mention is that this is my overall reaction, all right? So it is then the elementary steps are the steps to make the overall reaction. And so what's my rate determining step? Well, which one will follow, in a sense, the experimentally determined rate law? And I think we've already talked about this. If I'm looking at step number one, I have two NO2s, which would agree with this. Here I have NO3 and CO, and it doesn't agree with this. So my rate determining step is the first one, which brings us to an interesting question. What if my step two was actually my slow step? How would I actually deal with writing out the rate law if an intermediate is part of the slow step, all right? The answer to that is if you actually have only the intermediate, nothing else being made in the other step, in the preceding step, then you would substitute two NOs in for NO3, but that's not the case. So the AP will not give you one complicated like problem number 28 would be. Okay, we'll do some other examples showing you what happens if the slow step contains an intermediate. Okay, let's go to the next page. So problem 29 is a classic, kinetics kind of question, an environmental concern of the depletion of ozone in the Earth's upper atmosphere. Back when I was growing up, that was huge news. How can we stop the ozone depletion? Well, how can we slow it down? Okay, that's a kinetics question. It appears in a lot of different forms. So anyway, it says where O3, to your ozone, is normally in equilibrium with O2 and O. All right, so you have oxygen as a diatomic and this free radical oxygen. A proposed mechanism for the depletion of ozone in the upper atmosphere is shown below. So this is what they're thinking. So right here, this is what we'd call a chlorine, which originated from a chlorofluorocarbon, which was found in aerosols. And so they're saying that, using hairspray in the aerosol form is depleting the ozone, and then they're partially right. So what happens up in the atmosphere is really, really cold, and the chlorine would actually break off as a free radical itself, and then would attack the ozone, starting this whole process, okay? And you're going to see that there's a little problem with that, okay? It would only take a little bit of chlorine to make this whole thing work and be, catastrophic, if you will, for the ozone. So it says, write a balanced equation for the overall reaction represented by step 1 and step 2 above. All right, so just like Hess's law, remember Hess's law? Just like Hess's law, what are some things that we can cancel out? Well, I notice right here, I see this chlorine monoxide here, all right? That can cancel those guys out, but was there anything else I can cancel out? Yeah, I can cancel out the chlorines, okay? So what's my overall reaction? Well, I take an O3 plus an O, and I make what's left, 2 O2s, all right? So it's not necessarily a bad thing that we're making oxygen gas. There's more for us to breathe, but what happens is that we're gonna have more damage of the UV radiation without the ozone, so it is a problem. And it says clearly identify the catalyst. What's a catalyst? It's going to make the reaction go faster. All right, so what's the catalyst? Well, write this down. A catalyst is first consumed and then created again. It's the opposite of an intermediate. The CLOs are your intermediates. They are created, then consumed, so you never really see them. But the chlorine is first consumed, then created. Why is this so important? Because you keep creating a chlorine to attack the next ozone. And it gets used up in the, in the step 1, and then it's created again in step 2. So now you have even more chlorine to attack another ozone. So my catalyst is chlorine, okay? And what's the intermediate? I've already referred to it. It's your CLO. It is created, then consumed. So think of intermediates and think of catalysts are opposite ends. Okay, so maybe you wrote something down where you have catalyst is used up, then created, and intermediate is created, then used up. Okay, so it says if the rate law of the overall reaction is found to be KO31CL1, determine the following. Okay, so that's your slow step. Well, what's the overall order of the reaction? And this is where you just add up your powers, add up your superscripts. So what's 1 plus 1? The answer is 2, all right? And II is really important. What's the appropriate units for the rate constant? We've done this before, but it's a good review of what you should know. So this is what I did. Okay, here's the rate. That's molarity over second is equal to a constant times molarity times molarity. Okay, solve for K. All right, so K is equal to, all right, molarity over second, that's this one. And how do I get these M's over here? I'm going to divide them, aren't I? I'm going to divide by M, divide by M. And what do you notice is going to happen here? Okay, can we cancel out one of these and then one of these? And the answer is yes, I can. So what am I left with is K equals 1 over molarity second. So the last question is the rate determining step of the reaction along with the justification. So go back and look up here, okay, which one of these, either step 1 or step 2, corresponds to what we learned here is the overall rate of this equation. And hopefully you got step number 1. Why? Because the reactants and their coefficients match the rate order. So what does that mean? The rate order, there it is, O3 and Cl, they're both in step 1 and they both have coefficients of 1. Okay, I'm pretty much done here, so don't wait to be great.